Okay, now we're moving forward into some applications of exponential functions. And one of the big ones that we use a lot is compound interest. So the first introduction I want to give is just a little bit of language here. We are going to assume that we have an annual interest rate. And so, for example, if I were to say 3% interest, we're going to put that in decimal form. So it would be 0.03, not 3. T is always going to be years because we're just going to focus on annual interest, so T is years. And then A represents the current balance in the account, which includes what you started with and all the interest that it earned. And P is the starting value. It's basically the money that you invested at the beginning. Now, compounding means how often the bank will stop, compute the interest, and then add it into the account. And the more that you compound, the more money that you make because you end up getting interest added in over and over again more often, which means that every time you earn interest, you're earning a little bit more than if we didn't compound. So, first of all, if I have an account that's $20,000 in the account, this is my example, then that is what I'm starting with. So for all of these, that's going to represent my P. My annual rate is 4.3%, so my R is going to be that number as a decimal for all of these. And for each of these questions, I'm trying to find the balance after 10 years. So T is 10. And you'll see that all of those are variables that are in the original functions. Now, there is one additional function when we have n compoundings per year, and that is, what do we mean by n? And n represents number of times interest is computed and then added into the account. And when I give you the information in words, you'll have to find out what n is. So quarterly means that we compute and add it into the account 4 times a year. Monthly means we do it 12 times a year. And continuously is when we switch to the other formula. So now I want to also point out that for this, I don't really expect you to have these formulas memorized. I will have to check the WebAssign, but our next test isn't going to be proctored anyway. Just keep track of whether on WebAssign they include this formula or whether or not you might want to keep it on a reference sheet nearby for yourself. So let's go ahead and plug these guys in. For A and B, we're going to use the formula A equals P times 1 plus R over N to the NT, which for quarterly is going to be 20,000 times 1 plus 0.043 over 4 to the 4 times 10. And that leads to approximately $30,674.68. Now, I just want to point out that anything beyond the $20,000 that we started with is interest. So we've earned about $10,674 in interest over the course of these 10 years because 4.3 is a pretty good interest rate. We started with a lot of money. Now, this is not going to be dramatically different when we change how often we compound, but we will find that as we compound more often, we do get a little bit more money earned in interest. So for this one, everything is the same formula, same P, same R, but N is now 12. And that leads to approximately 30,721.53. So again, we earn more than $10,000 interest. It's a little bit more than when we compounded quarterly, but not, dramatically more. And our last example right here is going to be compounding continuously. And notice that compounding continuously uses the other formula. So we don't actually have an n for this because there is no n in this formula. We simply needed p, r, and t. And this is the first use that you're seeing of our natural base, which is e. So this is going to equal 20,000 e to the 0.043 times 10 for 10 years, which will approximately equal $30,745.15. And continuously is a little bit hard to imagine, but the idea is that they're just constantly computing and adding an interest, that there's no stopping. So our next application on the next page is radioactive decay, and that will be the last page in this lesson.